So welcome everyone to a new seminar. Today we have Marco Fiore with us. Marco Fiore is a research associate professor at IMDEA, where he leads the network's data science groups on research activities, the interface of mobile networking and applied data science. He's also co-founder and CTO at Net AI, a network intelligence company. And today he's here to talk us about the connection that characterize mobile network traffic and user population traits. So Marco, when you want, all yours.
Thank you very much, Patricia. Okay, let me share my screen. Do you confirm that you see my screen?
Yes, perfect.
Very good. So let me put this full screen. Okay. Yeah, so thank you very much for the introduction and thanks for having me today. Yeah, as you were saying, I'm going to talk about relationship between mobile network traffic and populations. But before I start the actual talk, let me make some advertising about where I work and who we are a little bit. For those of you who don't know, IMDEA Networks Institute is a public research center located in Leganés, Madrid, actually, 10 minutes walking distance from University Carlos III in Madrid, the Leganés campus. And the main focus of the institute is, research in telecommunication, computer networks, systems mainly. It's a relatively young institution that was founded 15 years ago, but that quickly grew and is nowadays, I guess, one of the leading research centers in Europe in the field of computer networks. At IMDEA Networks, I'm leading, as Patricia was saying, the network data science group, which was actually founded a couple of years ago when I joined the institute. And joined with a group of PhD students, postdocs. We're working on applying data science tools to network systems. So let's say our core business is designing network intelligence, so analyzing and characterizing network data traffic, in particular mobile network data traffic, and using the insights we get to develop models, data-driven models for network management, resource orchestration, control, scheduling, or network functionalities. But aside from that, having worked with mobile network metadata now for quite a lot of years, I became increasingly aware of the richness of this data, and the fact that you can use it to design and feed nice algorithms for network management, but potentially you can do much more than this. And so part of our interest as the NDS group at IMDEA Networks is on trying to exploit or use mobile network metadata for tasks beyond computer networks. So actually, the talk today is exactly about that part of our activities. And as the title of the talk says, I'm going to look at two phenomena, the dynamics of human populations and the dynamic of mobile network traffic that are deeply and naturally intertwined, because of course, in the end, mobile subscribers are people. And so the traffic they generate essentially is strongly related to the dynamics of the mobility, the activities, the endeavors of the population, of human populations. Nowadays, we start to have access to substantial data collected in operational mobile networks that allows studying the relationship between those two phenomena at scales that were not possible before, including looking at whole cities or even whole countries at once. And in the talk, I'm going to look at two different perspectives. Actually, the talk is in two parts. The first part, I'm going to look at, let's say, the direction from network traffic to population dynamics. And more specifically, I'm going to discuss how mobile network traffic metadata can be used to estimate population density. In the second part, the relation is let's say, reversed. And so I'm going from the population to the network traffic and discussing how population density information is related, is connected to individual network traffic consumption. So let me start with the first part that is essentially focusing on estimating dynamic urban populations. And let me start by defining what population density is, which is fairly obvious, but it's just a starting point nonetheless. So population density is a measurement of a population per unit area or unit volume, which in our case, as an example, is applied to humans, to individuals. So, well, since I like a lot, fancy graphs, fancy figures, here you have a map of the population density in the United States, courtesy of the Time magazine, where you can see, where people live essentially in the US, with higher spikes denoting larger conurbations in the country. This type of information is collected in, let's say, developed countries through censuses, registers, and so on and so forth. We will talk about this a bit later. But in many countries, developing countries, this type of information is not so easy to find. And so there are initiatives worldwide to gather information about population density, about where people live in a country. Initiative like WorldPop. So this is a map collected by that initiative in Uganda. In the talk, I'm specifically going to focus on urban population density, which is exactly the same concept, but it's applied to metropolitan areas only. And urban population density is an extremely useful piece of information that can be used for a number of applications that go from urban planning to designing transportation systems, analyzing social segregation, monitoring evolutions in demographics, or engineering better and more sustainable mobility, and so on and so forth. But again, the concept is exactly the same. So if we take a city like, let's say, the greater New York City area, we can look here at the population density, the number of inhabitants per square kilometer, or in this case, square mile, since we are in the US, measured by, in this case, census data at the level of tracts, which are small administrative units that are used in the US for demographic purposes. This map is provided by Social Explorer, which is a nice website providing this kind of visualization. But the idea is that different areas of a same city are characterized by different density of inhabitants. Now, how do we collect, how do we map population density today? There are both traditional and advanced approaches to do that. Traditional approaches include national censuses, registers of population, or even local surveys in some cases. And those are traditional in the sense that are pretty manual processes, and they suffer from a number of limitations. Essentially, they are very time consuming to run. They are very expensive to run. So as a result, they depend a lot on the engagement of the population. And so they are run only sporadically, even in developed countries, typically, once every 4 or 5 years, with the result that the data is often outdated, is sometimes unreliable because, again, it depends on the engagement of the population. In many countries worldwide, is not available at all. So actually mapping population density is an open research problem in geoinformatics. And there are more advanced approaches to address this problem. In many other fields, deep learning has led to a number of breakthroughs in this specific, let's say, subject. And in particular, using deep neural networks, applying deep neural networks to high definition satellite imagery has allowed mapping population density at much larger scales than before, and in a reasonably accurate manner. So, as an example, Meta, which is sorry, former Facebook, has fully mapped the population in basically most of the countries in the world at a resolution of 30 meters, which is pretty good, and made this data available in their data, through their Data for Good initiative, using exactly this approach, so deep neural network applied to satellite imagery. Now, this is not, the definitive solution, and we will also discuss why. But as a starting point in my talk, I want to discuss how we can do something similar, so mapping static population densities using information that is available in the mobile networks, can be collected from mobile networks. And we start from a legacy power law relationship between population density, so number of inhabitants per kilometer, and mobile network traffic volume. So this is a relation that has been identified by a number of works in the literature. And essentially it says that rho I, that is the population density at one specific area, location I, is a power law function of the volume of mobile network traffic observed in the same area. Okay. We had access at the time when we ran this experiment to mobile network metadata collected in an operational network in Italy, covering multiple cities of the country. And we actually tested first this relationship with the data we had by checking, the correlation between volume of voice traffic, volume of text messages, whether they were incoming or outgoing, also internet traffic that is not displayed here, and checking, if this power law relationship was holding for our data as well. And it did, in the sense that you can see here also that, there is this, the scales are logarithmic, so there is this power law relationship between the two metrics. But the relationship is also pretty noisy. You see a high variance around the, let's say, typical pattern, typical behavior. And a first thing we did in order to improve this model was looking at the different type of metadata. So not looking at total voice calls or total in volume of internet traffic or text messages, but something that is called presence metadata. That is, again, can be easily collected from mobile networks by looking at the location at where individual users are seen over time. Essentially, given one specific user, the presence is computed as follows. The user is observed at a number of locations over time, depending, on when the user interacts with the network. At each time the user interacts with the network, he or she can be georeferenced. Its location is known in the sense that it is associated to the base station that is actually serving the user at that point in time. And what we can do is assume that a user stays at the last location it was seen at by the network until the moment a new event at a different location is generated by the user. And by doing so, we have a very rough approximation of the user mobility, where essentially the user jumps from one location to another when events at different locations are recorded by the network, which again is approximate because, of course, the user can move in between those events recorded by the network, and also movements are, of course, not instantaneous in reality. It's a rough approximation of the mobility of the user, but it gives us an idea of where the user is at all times, which allows us to compute this presence metadata that is essentially obtained by quantizing time. So dividing time into intervals. For this study, those were intervals of 15 minutes. At each 15 minutes, we could count how many people, how many individuals were associated to a given antenna, so located in proximity of the antenna. And then by using the presence information as the sigma variable, let's say in the equation you have on top of the slide, we obtain a cleaner correlation, no, between this presence again and the census population density. So this seemed to be a better type of metadata than raw traffic volumes for modeling, for capturing the census population density. Still, the relationship is quite noisy, so we run a number of denoising approaches. First was filtering by time. So of course, since we are trying to model census population information, so let's say the number of inhabitants per square kilometer, the correlation between the presence metadata and the census data it was higher overnight, when subscribers are actually at their own homes. So we actually fitted the model by only looking at data between 4 a.m. and 5 a.m. That was the hour during which we had the highest correlation. We also filtered out weekends and holidays because at those times, essentially, users have a very different behavior than in regular working days. And also, they tend to be less at home overnight than during weekdays. And we also filtered out some outlying cells by running an outlier detection algorithm. We find out that some cells, some locations were producing consistently outliers in our system, and those cells were typically located at the boundaries of the geographical area denoting or containing each city in our data set. And that was due essentially to the fact that cells located at the border were creating border effects, in the sense that the antennas at those locations were probably covering population beyond the area that was not was captured in the census data, but not was not captured in the census data, but was captured in the by network traffic metadata. So, but excluding outliers essentially, and doing these filters I was mentioning, we could polish and clean the model, and finally obtain something reasonably accurate. So this is the overall performance, let's say, of the model. When looking at different types of land use separately. So essentially for each city, we identified different land uses, the main purpose of the area in terms of whether it is a residential area, office area, touristic area, and so on and so forth, and test the quality of the model in those locations. And we find out that for residential areas that actually are the most common type of land use, they cover 70 to 80% of the total surface of the cities we looked at. We obtain a reasonable accuracy with a coefficient determination of 0.8, less than 9% error, and a significant improvement over previous model that were using, not presence, but other types of mobile network metadata. The quality of the model degrades when we move away from residential areas, and this is very expected because people are there. I mean, people who are in office areas, touristic areas, shopping areas overnight. They tend to be there for other reasons than staying at home. So the correlation of the model becomes worse. An interesting observation is that the model is actually sort of reusable across cities. So if we train one model, the model in one city, so we fit the power law essentially in one city, and then we use it to predict the population density in another city, we obtain, of course, degraded results, but still usable with less than 10% or around 10% error overall. So here results concern the 3 cities we had access to in Italy, Milan, Rome, and Turin. Okay, so far so good. We can sort of use mobile network metadata to study those population densities, which may be useful as an example for developing countries where the mobile network phone data can be available, is actually typically available, can be collected by the operators, but the census data is not available for difficulties in running censuses. So actually this is helpful there. It's not so helpful in developed countries where census data is actually there. No, actually we are using it as our ground truth. So in that case, the model is a bit an exercise, not something that is useful in practice. What is useful even in developed countries is being able to track dynamic populations. So this stems from the consideration that population density is a time-varying phenomenon. So it's not static or over time. Actually, if we look at static population density, so the number of inhabitants per square kilometer that is captured by census data, by looking at the evolution of this information over long time scales of years, we already look at some type of dynamics. So let me give you an example here, is how the density of inhabitants, density of population, varied in 10 years between 2010 and 2000, in several cities in the US. And this is obtained by looking at, by a website that is called datapointing.net, by looking at census data collected in the country. So you can observe, and red color means decreasing population density, blue color means increasing population density. And so you can observe, the fact that Detroit was struck by a big economic crisis in those 10 years. And that led a lot of people to leave actually the city, especially the city center. In the same 10 years, Las Vegas grew a lot in its outskirts. Or that was also the period when Hurricane Katrina struck New Orleans. So you can see really whole neighborhoods, actually a large part of the city losing essentially a lot of inhabitants because they didn't have a house anymore there. So this is very interesting, but these are very long time scales, not years. And if you think about it, population density undergoes much shorter timescale dynamics because people move. They leave their home in the morning, they go to work, they go to different activities over the day, they come back at home at night, maybe they go out and have a beer after that. So timescales at which fluctuation in dynamic population density occur are actually in the order of minutes. And there is no way we can capture this kind of fast timescale dynamics using census data, but not even using a very complex, deep learning solution applied to satellite imagery. Exactly because satellite imagery, they vary over those long time scales of months or even years, but not at minutes. So understanding or being able to track this variation in population density at minute time scale, this is a very nice, problem. And interestingly, mobile network metadata has a granularity, can be collected at least at a granularity that allows us to achieve the time scale of time, follow essential order of minute variations. So the question is how do we do that? And more precisely, the big challenge is how do we model daylight hours? Because we know that overnight, we can easily train a model using census metadata, but during the day, the distribution of people is going to change and is not going to be related to the census data. It's going to be related to where people work or where do people go over the day. So we don't have any ground truth anymore to train a supervised model like we did with the static population density before. And a simple approach could be to just train a static model overnight. So taking essentially the model we discussed before and using it over the day. But then that model captures correlations that may hold overnight and not during the daylight hours. And actually, just next, I show that this is the case. So doing this may result in essentially wrong conclusions, wrong mapping of the population. The approach we took is that of relying on a yet another type of metadata that can be collected in mobile networks, which is what we call user activity or user activity level and denoted by lambda. In the results I'm going to show, we are, let's say, defining the user activity level as the average number of calls per person per hour, measured at each location, at each antenna or at each location. But in fact, we tested a number of other definitions by changing calls by text messages or internet traffic, and the results didn't really change. So actually, the user activity level can be defined as, you know, the level of engagement of individuals. So how much each individual on average interacts with the mobile network. And this is a time varying, let's say, measure. As you can see here in the plot, over a typical day, the value of lambda, well, changes, and you have much smaller number of average interactions overnight and higher over the day, over daylight hours. So what do we do with lambda? Essentially, the key observation is that this lambda value changes, even if slightly, overnight. So this allows us, and we know that overnight we can trust the census information, okay? So the catch is that we can train a number of static models of the population using the census metadata as the ground truth, and checking how those models, how the parameters of those models, so the alpha and beta parameters of the power law of models trained at different hours overnight, correlate, if they do so, with the user activity level. Okay, so essentially, we build a lot of different static models of the population, of the census population, and look at how their alpha and beta parameter relate to lambda. And quite interestingly, we find that there is a very strong correlation between those. So both alpha and beta can be described pretty nicely as functions of lambda. The function change depending on the city, so the different colors are different cities, so the model is not reusable across cities. But in a same city, we can actually have, you know, that type of relationship. And then now, if alpha and beta are actually functions of lambda, that means that we can revisit our power law model and transform it into a multivariate model, where we have again the same relationship as before, in the sense that rho, the population density, is a power law function of sigma, the presence metadata. But instead of having a fixed alpha and a fixed beta, we have now two functions of lambda. And lambda is something that varies over time. And assuming that the relationship between alpha and beta that we observe in the plot on the right remain varied across the full day, including during daylight hours when lambda is higher than the lambda we observe overnight, then we can imagine that this model lets us capture population density at any time, okay, including over the day. So this is an assumption. It is based on the fact that, you know, those relationships we see on the plots actually continue to stay the same for higher values of lambda, for which we don't have any ground truth. So it's still, the model is still at the level of an hypothesis, but we can try to validate it by using, you know, some point, well, ground truth that we have at specific points. And those points for us were sports events. So since we were looking at Italy, those were essentially football matches. And for, you know, we collected information about the number of football matches played in, you know, Milan, Rome, and Turin. And for those football matches, we could gather ground truth information about the attendance, no, number of people actually at the stadium who went to the stadium for the match. So essentially, what we could do is compare the ground truth information with the estimated attendance obtained by just looking at the mobile network metadata, using the multivariate relationship that I was discussing before. And what you obtain is, again, a reasonably accurate model. There you have, on the x-axis, the different football matches. On the y-axis, the relative error. And the green model is, you know, a previous model proposed for dynamic population density that was using a deep learning approach, but trained on census population data only. So the model, a state-of-the-art model, making the assumption that a model trained overnight can also be used over the day. The red bars are the performance, represent the performance of our model. And as you can see, it's pretty evident. No, our model actually was quite better. The error is around 10% versus 20% of the other model. The performance is not homogeneous across matches. So there are some matches for which we can predict better, some for which we can predict worse. But overall, the average error is 10%, which is aligned with the error we had before when looking at static population density. So our hypothesis here is that the error comes really from is not a limitation, or at least not mainly a limitation of the model, but it's really a limitation of the data. Once we have this, okay, we are sort of confident about the quality of the model. Then we also exploited the model by looking at by just looking at mobile network metadata, how population density based on the network metadata evolved over day in the target cities. So we were looking at commuting patterns in the morning and the afternoon, or an interesting use case I want to show you, the emergence of large social events. So this is a public march happening in Milan. The four maps refer to four different snapshots, let's say, of the population density. They are represented as Z-scores in order to evidence difference with respect to the typical day. And I think the four plots are half an hour apart from each other. So the first plot on top left shows the people gathering at the place where the march was starting from. Then the second plot, top right, shows the march progressing towards the city center. The bottom left plot is the march reaching the Duomo Square, the center of the city, where the march was ending. And then the last plot, bottom right, is the march essentially dissolving and people leaving it. And apart from visualizing, graphically the special behavior of the march, we can also quantify, by using the model, the number of attendees, number of participants to the march. And in this specific case, we estimated that at its peak, participation reached around 37,000 people. And we compared actually this number, I remember, with the estimates provided by the organizers, as well as the let's say, local police office. And we found out that our estimates were actually laying in between those, so which is sort of reliable, because those are typically an upper and a lower bound. So to conclude on this part, I think the bottom line, the takeaway message is we can use, in fact, mobile network metadata to estimate static and dynamic, more importantly, population density. We can do so with a reasonable level of accuracy. And I also want to stress that when we carried out this study, we were using mobile network metadata that was fairly inaccurate. So for those of you who have worked with that type of metadata in the past, we were working with call detail records, which are very well known to suffer from low spatial resolution of the location information. They are very sparse in time. They are irregularly distributed in time. So let's say that the metadata was sort of low quality. Nowadays, mobile network operators are improving their, let's say, capabilities to actually monitor the type of data in the network by, as an example, collecting signaling information at the radio access. And so repeating the experiment with that type of data, which is something that hopefully we plan to do in the future, I'm pretty confident would result in much better performance. Okay, jumping to the second part of the talk, where we go the other direction, from population to traffic. Here I'm going to focus on second-level digital device. So let me start again with a definition. what's a digital divide? It's a gap between people who benefit from ICT, information and communication technology tools, and people who do not. Okay. Now, this definition is pretty well known, but actually, what's less known is that there are multiple levels of digital divide. The first level of digital divide is the typical, let's say, acceptation of digital divide, is the most visible one as well, and it refers to access, to the possibility to access or not the digital services themselves. So this is related to, you know, availability of the infrastructure or affordability of the devices, and typically is a divide that characterizes developed countries versus developing countries, or in some cases, you know, urban areas and very rural areas. However, there's also a second type of, and well, yeah, okay, this first level digital divide is typically supposedly closed in developed countries. There's also a second level digital divide that concerns quality of use rather than access. So this is less visible, let's say, and it refers to the fact that people have the same accessibility, the same level of access to the technology, to the ICT, to the mobile services in our case, but they use those services in a different quantity or with a different quality. So this doesn't depend on accessibility. No, everybody can afford a mobile phone. Everybody has access to a broadband mobile network, but then people use those services in different ways. And this is more related to the digital skills of people, the fact that there is a divide between people who know how to use these tools and people who do not. So we're actually going to study a potential case of second level digital divide in France. So it's a developed country in Europe. And the sentence there summarizes a little bit the focus or the scope of our analysis. We're going to look at nationwide mobile service consumption. So nationwide means that we're looking at the whole country at once, and the spatial granularity of our analysis is individual cities. Okay, so we're going to compare smaller town villages to medium-sized cities to large metropolis in the country. But the unit, for us is the city. So samples are collected at whole city level. And we're going to compare essentially across different urbanization levels. Then we're looking at mobile services, which means that we focus on cellular network usage. So all considerations I make are only related to cellular, usage. And we're going to look at consumption. So the divide we're looking at, or the whole analysis in any case, is related to the volume of traffic consumed per capita in the city. So we're not going to look really at a quality of use divide, rather at a quantity of use, how much traffic people generate. The study is based on data, of course, and we have two main sources of data. The first one is the mobile network traffic information collected by Orange, that is a leading operator in France that has over 30% market share in the country. So we have, pretty good coverage of the population in the country, in each city. And what they provide us with are aggregates, daily aggregates of the total volume of mobile traffic consumed at base station level. And we complement that with information, demographics information about almost 5,000 communes and over 2,000 urban units. So those are two different definitions of city that we use across, in parallel, let's say, across the whole study. And this is because, there is no commonly accepted definition of city. So we thought of considering two different potential definitions. And and use them in parallel to check, the robustness of the whole methodology to the definition of city. In both cases, we are looking essentially at all areas in France that have a population of at least 2,000 inhabitants. And we're covering between 70 and 75% of the total population of the country, depending on the definition of city there. In order to bring together the mobile network traffic data and the demographic information, we need to perform a spatial mapping. And we do so by first modeling the coverage of each base station as the corresponding Voronoi cell. This is a very common assumption in the literature, according to which essentially each user is connected to the antenna that is the closest geographically to its location, and the users are uniformly distributed over space. These basically are the assumption under this notion of Voronoi cell coverage. As an example in the figure, for antenna I, we have the surface that is covered by antenna I with a uniform distribution of traffic, SI. And the administrative surface is, the borders, the contour of the administrative surface that can be the commune or the urban units. J in this case is something we can get, easily from national databases. And then once we have both, what we can do is a weighted spatial interpolation, according to which we assign a portion of the traffic observed at antenna I to the administrative surface J, based essentially on the fraction of the Voronoi surface that overlaps with the administrative surface. So we do this for all antennas and communes, and we essentially map traffic to each commune. So at the end of this process, we can know the volume of traffic that is associated to each commune. Once this interpolation is done, the first thing we want to do is essentially to study this relationship once again between traffic and population. So what's the law relating traffic and population? And we want to do so at national scale. Even though the scale has changed, it makes sense to start again from a power law, because again, the relationship has been shown to work at different scales. So all the works I discussed in the first part of the talk looked at city scales. So they essentially looked within a city, different neighborhoods, or different base stations, and found out that this power law relationship existed at that scale. Here we're scaling things up, so we're looking at the whole country, and there have been a couple of studies that have shown that when the spatial granularity is whole regions, whole departments in the country, then again we have a power law relationship between the traffic consumed and the population density. Nobody has looked before at individual cities as we do, but again, since this law seems pretty robust to scales, to different geographical scales, it makes sense to start from this again. And so this is what we do. Essentially, we match the mobile network traffic, the total mobile network traffic recorded at a city, to the population of the city, so the total number of inhabitants in the city. Again, through a power law, of course, in this case, it's reversed, and we look at traffic as a function of the population. We also have to face some modeling challenges in this case. So this is again a bit of denoising in order to make the model more accurate. We only look at working days. We remove some artifacts that are due to the spatial interpolation. So by running again an outlier detection algorithm, we can identify a number of communes or urban units that have a strange outlying behavior. And by removing a few tens of communes, which map to less than 1% of the total population in the country, we are actually able to improve the quality of our model. And by looking at the outlying communes that we remove, we see that those are unfortunate cases like this one, no? Where essentially we have a set of base stations that cover a commune that is the dark area at the center of the figure on the bottom right. And what happens in reality is that all those antennas, the white dots, they have azimuths such that the antenna illuminates the actual commune. So they point to the commune, they point to the city. But the Voronoi approximation is such that the traffic is assumed to be uniformly distributed over the Voronoi in orange for each antenna. So when we do the weighted spatial interpolation, only a tiny fraction of the traffic associated with the antenna is actually mapped to the commune, whereas a large fraction of the traffic of the antenna is actually generated in the city. So those are limits of the spatial interpolation. We can't do much about it because we don't have information about the azimuth of the antenna as an example. So the best thing we can do is actually remove those samples from the dataset because they are biasing the results. Also, data is highly heteroscedastic, which means that, as you can imagine, in a whole country like France, we have hundreds and hundreds of small villages and tiny towns, but only one Paris and one Marseille and one Lyon. I mean, very large cities. So we have, a lot of data gathered around low population density and only few samples for high population numbers. So this causes the fitting to fit well the head of the distribution where you have low populations, and not caring a lot about fitting the larger cities, which are actually as important, if not more important to us than smaller ones. So to address this problem, we use a commonly adopted solution that is log binning the data. And just to give you an idea, a model fitted on the raw data gives a curve here on the plot that is the yellow one, the gold one, where we see that the quality of the model decreases significantly when we look at larger cities on the right part of the plot, while fitting the model on bin data, log bin data, gives us a more homogeneous quality of the model across different population sizes, across cities that have different population sizes. So, in brief, we do a number of denoising, adopt a number of denoising approaches, and thanks to these, we can fit the model and obtain something like what you have on the plot here on the right, which is population versus the normalized mobile network traffic. The gray dots, the small, tiny gray dots, are the individual cities, sample for individual city per day, actually. The black dots are the bin data points. And then the yellow line is the fitted model on the bin data. So first observation, the power law hypothesis holds also in this case. So we have a nice fitting with decent Pearson correlation between the model and the data. So even at this counter scale where our data points are cities, the power law works. More interestingly, if we look at the parameters of the power law, and in particularly at the exponent of the power law, we see that this exponent is consistently above 1, consistently across a number of tests that I will discuss later on. But yeah, the exponent is above 1. An exponent above 1 means that we have an emergent behavior, or if you want, a divide in the quantity of use across cities of different size. In other words, the larger the city, the higher the amount of network traffic that is consumed individually by the inhabitants of the city. Okay. This is not easy to observe in the scatter plot or in the fitting. It's really a property of the exponent. But to give you a number, based on these results in the plot we are looking at, the typical user in a city of 1 million inhabitants actually generates 2 times the amount of mobile network traffic than the average subscriber in a small town of 10,000 people. Okay, so there is actually a divide. People are using much more mobile network services in large cities than in small towns. An interesting question is whether this is affected, this is determined or caused or has some effect on a per service level. So we have access through the operator at traffic disaggregated across services, so we can know how much of the traffic generated in each city is actually contributed by each application. So we repeat the experiment on a per application basis to study, as an example, if this effect is only due to some application. I don't know, people actually use YouTube much more in large urban areas than in smaller villages, and then this explains the divide. It's just YouTube. All the other applications don't show this behavior. So to check if this is the case, we rerun the experiment, the same test, by looking separately at the traffic generated by each service among the top 50, the 50 top services, the most popular ones, those that generate the most traffic and have the most users. And actually, what we find out is that this positive return to scale, this emergent behavior, so this exponent higher than 1, is there for all applications. All applications have invariably an exponent higher than 1. So this divide is not affecting a few applications. It is actually homogeneous across all the applications, although the value of the exponent varies quite a lot. So for some applications, the value is just above 1, meaning there is some divide, but it's small. For other applications, the divide is much higher because the value of the exponent is 1.4. So there is a substantial difference in the volume of per capita traffic generated for that application in large cities and smaller towns. So the let's say intensity of the phenomenon is diverse across applications, but the phenomenon is present for all applications. Okay. Now we are lucky enough that we have access to data for multiple years. Okay, so we can actually study the evolution of this divide between 2014 and 2019 by fitting essentially the model in different years with data, mobile network traffic data, and with population data, in each year. So what we find out is that the trends are consistent. In the sense, if we fit the model across the different years and we compare the parameter k, that is the multiplier, not the exponent, the multiplier of the power law, we find out that this k is growing over time. So on the x-axis in the plot on the right, you have time, years. We have some gaps because we don't have data for all the years, but we missed 2015 and 2018. Still, the trend is pretty clear, and it's the same no matter if we look at communes or urban units. K is growing, the multiplier k is growing, and k maps essentially or gives us an idea of what's the average traffic generated per individual. If you want the semantic meaning is that's the traffic of a person living on its own, completely isolated from anybody else, would generate. And this is growing, and this is very much expected, because as time passes, we are using more and more mobile devices, mobile services. We're relying more and more on that, and also we're using applications that are increasingly traffic hungry, like video services, streaming services, and so on and so forth. So it's normal that the average traffic per individual grows, and this captures that phenomena very well. But this is not unexpected. It's actually very much expected. Then we look at the exponent, and there we find out something that is not so much expected. That is to say, the exponent is always higher than 1, fine, but it's also growing over time. Okay, and if you think about it, that means that the divide we were observing before is not being closed over time, but is actually widening over time. So people in larger city, living in larger city, are consuming more and more data in comparison with people who living in smaller towns. So to give you a representative figure, the per capita traffic, the average per capita traffic, has been rising 26% faster in a commune of 1 million inhabitants than in a town of 10,000 inhabitants. So we have this divide in terms of quantity of mobile network usage that is actually widening over time. And this is the same representation just over space. We're looking at a map of the compound annual growth rate at different locations. So at all the 5,000 communes that this is urban units actually over France that we are monitoring. Darker color mean higher CAGR, and actually all the darker spots are located in correspondence with the largest city in the country. So you can see Paris, Lyon, Marseille, Lille, Strasbourg, and so on and so forth. And the map gives us the same message. So the CAGR has grown at 75%. The CAGR is 75% between 2014 and 2019 in larger cities, whereas it is only 30 to 50% in minor centers. Now, this was a bit puzzling. No? When we find out this, we were a bit astonished because you're supposing that this type of divide are being closed, but no, actually it's the opposite. So we tried to explain it somehow. And the first thing we were looking at was mobile broadband coverage. So how diffuse, how spread is 4G over the country? Since I recall that we are only looking at cellular traffic. So here you have, a representation of the coverage of 4G over the years, 2017, 18, 19. We don't have data before that. And for each year, we have essentially the coverage, mean and standard deviation, positive and negative standard deviation for different sizes, let's say, of the city. Of course, we're not showing all sizes. We are actually grouping cities depending on their size. And essentially what the plot says is that the coverage has been improving over the years. So less urbanized places, more rural towns and cities, where experiences are not perfect 4G coverage in 2017, but in 2019 that gap was closed. So the message here is, over the years, the access divide, the first type of digital divide, has been closed completely. So in 2019 there is no digital first level digital divide anymore in France. 4G is pervasive, and yet the divide we observe in terms of quality of usage is growing. So the quantity of usage, is growing. So we're definitely looking at a second level type of digital divide. So access divide has nothing to do with this, and coverage cannot explain what we see. We tested a number of other social and economic indicators. We try to relate what we were seeing to income, to the presence of commuters, entering or leaving the commune or urban units, to the age of the population, by looking in particular at the fraction of people who supposedly are more active in terms of using mobile network services. But in all those cases, we could observe that over the year, patterns were pretty constant. So none of those indicators we were looking at was actually capable of explaining the divide, and more importantly, the increasing divide that we are observing with the data. So bottom line, in France at least, but we suspect in other developed countries could be the same. We are observing, a previously unknown, hidden, second level type of digital divide in terms of quantity of usage that we cannot explain this time. So, it's part of the future work. I hope not only by our group, but hope this stimulates also research, by other groups. Understanding why this is happening, I think it's a very, interesting open question. Okay, so let me wrap up. with a few considerations. So, okay, I'm not repeating conclusion, from the first two parts of the talk. I think I gave those at the end of each part. Just to mention, a few of the other things we're looking at in the group that are related to this part, of our activities, and there's the whole other direction about network management and so on and so forth. So one thing we, as you may have guessed by some of the discussion during the talk, this Voronoi representation of the mobile network coverage that is used nowadays to map spatially traffic and any other type of mobile network metadata is a bit annoying. It's a pretty inaccurate representation. So we are working on developing better models of coverage in order to help a better spatial mapping of the data. We're working on models that are improved and more explanatory for the tasks that I discussed during the talk, but also other ones like land use detection or trade area mapping. We're also studying models to generate synthetic mobile network traffic, because this type of data, is not really very much available. Operators tend to have, tend to be very careful about sharing that. So we're working on generating synthetic data sets that can be made publicly available for search. And as many other people around the world, since we are in COVID times, we're studying impacts of COVID on mobile network, let's say, usage. One interesting consideration I would like to make is that all the studies we are doing in this direction with the group are built on aggregate metadata. So we actually only use data aggregated or at the antenna level, base station level, or in, let's say, level of city or neighborhood within a city, over intervals of time that go from minutes to hours to days. So essentially, we're aggregating information about hundreds of users without any possibility to track them. So I would push myself to say that the data is fairly privacy preserving. So actually, we can do a lot of very interesting things with mobile network metadata that is fully privacy preserving, assuming, of course, the aggregation is performed by the operator in secure premises and so on and so forth. And then I would like to leave you, with a bit of a message or a vision. I guess the things I discussed during the talk, but also the other things I'm looking at within my group, prove that mobile network metadata is a very rich source of information that can support very complex tasks and help solve very complex problems outside telecommunications. So a kind of message that I'm trying to push into my community, that is, the networking community, computer network community, is that maybe we should start thinking about designing mobile networks, so maybe next generation of mobile networks, 6G mobile network, so that they natively support remote sensing. So the idea is that the mobile network itself should be designed not only to transfer bits from one point to another, but also to use the information that is contained in those bits to feed remote sensing applications like those for population density estimation, land use detection, understanding social segregation, and so on and so forth. And this is actually an engineering challenge, because it means rethinking a little bit the architecture of the network, the functions that are implemented within the network. And so this is something we plan to do in the group, is develop remote sensing functionalities in programmable data planes, so that essentially we program switches, the actual hardware that is used in mobile networks, in a way that as the traffic passes by, the switch start computing, aggregate information and metrics and features that can be privacy preserving and can be passed to the upper layers of the network, and then to, service providers that perform remote sensing applications like those, discussed in the talk. And all this happens in real time. Now the information goes from the mobile network operator to the applications we were seeing in days or weeks or months. That makes it impossible to have a real time, let's say, type of remote sensing. But if we embed those functionalities in the data plane of the network, in the actual hardware, through which the traffic transits, we can actually hope to see those remote sensing application happen for real in production networks in real time. Yeah, so that concludes the talk. I would like to just thank the contributors to the research that was presented in the talk, and you have contact information, and I'd be very happy to answer any question. Thank you very much.
Thank you, Marco. Very nice presentation and very nice work, of course. So thanks. Now we are going to open for discussion. The people that wants to ask can directly unmute themselves, or I can read the chat in case you have any question. And actually there are one. Okay, so let me read a question. So Hadi is thanking you for the presentation, of course, and he has a comment of sneak peeks for further research can be consideration about return and churn mobile consumers versus our dynamic population.
So I would need, probably the person to elaborate a bit, but am I correct if I say that the question is about whether we can correlate churn with population, or let's say demographics information? Is that the point of the question?
Yes.
Yes. Thank you. Yeah. Okay. So that's a good question, and unfortunately, I don't know. I don't think I have an answer. Like in many of these data-driven studies, you don't know.
because my background is quality assurance in a mobile telecommunication service, and in the strategy team, we propose some research about how many return and how many churn for consumers regarding to migration between population in all over the country. It's very important for computation of the, for example, in payload. Payload is very important for network, the issue for mobile telecom.
Right.
And for example, very important to consider churn and return consumers versus population, and versus dynamic population for your presentation is very helpful and very good insight, but very hard to exact computation. It's need to really check.
Yeah, right. That's what I was going to say. Like in this kind of data-driven studies, you don't know what to expect or what's going to be the quality of your model or correlation until you look into it. It's data-driven, so data tells you whether the model is good or not, etc. Up to which point you can refine your model, denoise the data, and so on and so forth. And I've seen that, I've seen in the literature models of churn or return that are based on much more fine-grained information than the kind of information I discussed in this talk, or more generically, dynamic population, because those works were looking at, individual subscriber features. So given that my subscriber has this number of features, what's the probability that it will change operator in the next 1 year? Now, I think that's feasible. There's a bunch of work that have been done this in the literature, but if you move to a much larger scale and you say, okay, I want to model the churn of a whole population, churn ratio of a whole population based on very high level aggregate statistics, like dynamics of that whole population. I mean, of course, you're looking at a much more complex problem because the individual features now become features of a whole large population, and it may well be that you lose that accuracy that allowed you to build the individual model. So, you know, it looks like a very challenging problem. I do not exclude that some reliable model of the churn and return can be obtained by just looking at population level statistics. But again, I cannot commit to it until you know, I actually do the proper study. So if you're working in that direction, I will definitely be happy to, you know, hear from you in the future whether you succeeded in that or not.
Mm-hmm. Thank you. Thank you.
Yeah, sorry, not much of an answer, you know.
So thank you. I don't know if there is more questions, although I have one, so I'm gonna use the time. So you said that you were planning to use another techniques in order to overcome the Voronoi limitations. And what representation are you considering?
Yeah, so I would have hoped to have that, you know, published at this point in time, so that I you know, I could actually even present this during the talk, but fortunately it's not published yet. But the idea is that again, we are lucky enough to have access to ground truth information that is actual propagation data provided by the operator. So for each antenna, for a very large data set covering a whole country, we have information about the exact propagation information, yeah, the area that is covered by the antenna. And what we are working at this time is, you know, trying to identify simple models that, by just using information about the location of the antenna, can produce a coverage that is as close as possible to the ground source. And we already saw that you know, Voronois do not work. So actually they have a pretty bad representation of the coverage. And we are investigating a better data-driven model that can perform that spatial mapping. Fortunately, yeah, I cannot tell more than this at this time.
I'll read the paper when it's published.
Hopefully, finger crossed.
Okay, so is there any question?
Yeah, I see the.
Okay, they are reading.
Question, I think is Angel, right? Yeah, it's not publicly available, and that's precisely our point. Like, we would like to have a simple model that is capable of producing these representation of the coverage that is as close as possible to the ground truth, so that then we can release the model. No, we can make the model publicly available and say, okay, do you have information about the location of base station, which is something that is typically fairly easy to obtain, or that the operator release together with the traffic information? Then yeah, okay, use our model and you get something that is so much better than a Voronoi and decently close to the actual propagation. But yeah, unfortunately, the propagation data, actually, I think, you know, the students who are using that data, they had to sign a very restrictive non-disclosure agreement, like, according to which they will probably have to, you know, sell their house in case, or you know, lose all of their earnings in case they release the data or something like that. So it's, yeah. But I hope that once we finish the work, and if the model is good enough, you know, we can provide the community something that is reasonably good and much better than Voronoi.
Nice.
Yes.
So I guess there is no more questions. So we can finish here. So Marco, thank you a lot for
Thank
your
you.
presentation.
It was a pleasure. And, you know, you have my contacts there. I mean, anybody who wants to reach out, I'd be very happy to talk.
Okay. Thank you so much.
Thanks, everybody.
Bye.
Thank you, Marco.
Thank you. Bye, everybody.